Hey guys, gonna be doing a video on the finished SXB. If you guys remember, when I posted the original thread on SXB, I said I was gonna be switching to the larger package they offered in that IC that I was using to see if it was actually capable of performing better. And as you guys will see shortly, it's definitely a big difference. Here's just a quick setup. As usual, we have the load voltage, the current that's going to the diode, or the load going to the diode, input voltage to the driver, and how much the driver is pulling. Side note is my power supply is only rated for 5 amps, so being that it's only rated for 5 amps, it's not really capable of doing the job. So I'll be switching over to cells about halfway through this video. I did order a 20 amp power supply that should be here probably in 3 weeks from overseas, so I'll be doing a proper video when that comes in on this driver again, but just wanted to show this off really quick right now, show you guys what I've been working on. In order to turn this drive with this power supply on, I have to start off higher, and I'll turn it down. You can see we are the load's 4.8 volts, and you'll see it dropping. That's because the test load's heating up. Basically, it's the same thing for diodes. When your diode heats up, the voltage load of it will slowly drop, not as fast as the test load, because there's more heatsink on your diode, which will slow the voltage drop down. On the test load, and on this test load that I'm using, there's not that much heatsink. It is heatsink, but it's just not enough. You can see I have the driver set to roughly 2.5 amps. It does have a soft start feature that I'm playing around with right now, which is basically jumps up to 50%, then 90%, and then it ramps up from 90 to full current slowly. So as you can see, we're at 3.7 volts, and I already maxed this power supply out, but you can see it's still rock solid at 2.55 amps, or 2.5 amps we'll call it. So I'm gonna switch over to cells right now and get this meter out so I can show you the voltage. Also keep in mind there's a lot of wires running around here, and especially the supply wires, even though they're thick and rated pretty high, when you're using a supply, it's different when you're using cells compared to using a power supply. When you're using cells, you want the battery to be as close to the driver input leads as possible. You don't want to have it running 3 feet before it hits the supply, because before it hits the driver, because you will get quite a bit lossage, and it'll end up trying to pull more current out of the cell, and making your cell run harder. But this is just a quick setup just to show it off. It'll have no problem doing it, but there is some losses, and it does affect the efficiency of the driver due to having longer leads on the input voltage right now. First test we'll be doing is with this 26650 from overseas. These are not bad. Actually pretty good 26650s. I purposely didn't charge it, and also I want to mention that these are old cells, well over 6 months, well used cells, probably well over 50-100 usage. on heavy loads, you know, 10 amp loads. So they are well used cells. Like I said, I purposely didn't charge them, so this one's at 3.98 volts. You also got to keep in mind that cells do sag, unlike a power supply, so it's more of a real world test. And especially that these cells are old, they will sag more, because I don't consider these cells 100% anymore. And maybe at the end of the video I will show you a couple of these cells, of the difference of what they're showing on a load and not on a load. So first test, 26650 at 4 volts basically. You can see no problem. That's the ramp up that I was talking about on the soft start that I'm playing around with. So there you go, 26650 at 4 volts. And that's another thing I want to mention. If you plan, no one's going to be running their 9mm diodes, because this is what I basically designed this driver for the 9mm 445 nanometer diode. No one's really going to be driving their diode at 2.5 amps, because one, we don't know if that's a safe current yet, and there's not enough testing done at that current. Most of you guys are going to be running it around 2.2, maybe 2.3 amps to play it safe. So this is just showing what this driver can do above that, so you're sure that it's more than capable of doing the lower currents. And due to this driver having such a high switch, which is well over 10 amps, well over 10 amps, this driver has no problem doing 3 amps for 445 nanometer down to 3.6, 3.3 volts, no problem. It's probably more capable of doing up to 4 amps for 445 nanometer if you really want to talk numbers. So this is why I wanted to switch to the larger package, because there was no way that the smaller package that I originally was using on the SXB was capable of handling that type of switch. There was no way to control the heat. It would just heat up way too fast, and there was no way that you can dump that heat fast enough. So that's why I switched to the larger package. And it's definitely a huge difference, I can already tell. Before, I wasn't capable of getting more than 2.3 amps. Now I'm able to get the full max of what the driver can deliver, or the chip can deliver. So we're using a Panasonic 3100 mAh 18650, also well used, and purposely I didn't charge it also. So we are at 3.97 volts, basically 4 volts. And again, no problem. Alright, so now we're going to switch over to the LiPo and use an A123 26650. I originally bought these, they were used in a cell pack. As you can see the weld mark still there. So I rewrapped them because the casing was all messed up. But these are A123 26650s, and they were used when I bought them, and I used these in the Devil's Brother build, flashlight build that I did. So these were very hard used, but they should do just fine for now. And you can see the voltage is 3.36 volts. Okay, so 3.36 volts. It's already under 3.6 volts. So and connect it. Like I said, these are used cells, so and not charged at all. So you can see it's doing it just fine. The cell is getting warm. This cell should not be getting warm just yet off of this load. But as you can see, just fine, no problem. That was under 3.6 volts, so next up we're gonna do is an A123 again, this was bought brand new, but it's well over 1 year old. I use these also in that very high current, you know, pulling 15 plus amps on that Devil's Brother flashlight build I did. So these are at 3.3 or 3.4 volts. Same thing. See, 2.5 amps, no problem. Okay, so as you can see, that's under 3.6, so that tells you that it's more than capable of doing, you know, what our laser requirements are, and that's minimum 3.6 volts, which everybody craves, you know, which in my opinion should be 3.6, 3.7 volts, because typically it's 3.7 volts, and no one really puts their cells down that low. At least I don't. But that's what people want, and that's what I have to do for you guys. So now I'm going to show you the sag that these cells provide. And again, keep in mind, there's, you know, about 3 feet of wire running to the driver in between the cell and the driver, so there's definitely going to be, you know, some, you know, loss there. Typically you want to have the cell, you know, as close as possible to the input leads as possible, and as thick as input leads as possible, especially on this driver. Let me get set up really quick. Okay, first cell I'll show you is the 26650. Again, the without a load, this is at, again, 3.98, 3.97. Okay. Now, under load, so we're at basically 4 volts. Under load, we are at 3.72, nearly 0.2 volts drop under load. So you can definitely tell you do need good high quality cells, and you can see it dropping 3.7. Okay. The 18650s, there's a little bit less sag on these as well. Again, you can see the load on these. I mean, not under load is 3.96, and under load they're 3.55, 3.54, 53, 52. There you go. So you can see the sag there, almost half a volt sagging. Next up, we'll do the 18650 A123. Here is what it is without a load, 3.35 volts, and under load, 1 second, let me get under load. These are at 3 volts. You can see it's still delivering full current. So it's dropping about 0.3 volts. So basically what I'm saying is, if you plan on running this driver hard, you know, above say 2 amps, please use some good high quality cells. At least these 26650s, these are pretty good. I don't know what the True Ma is, but I've been using these, and they've been serving my purpose. And these 3100 mAh Panasonics. Any of the name brand 18650s should not have a problem, but these are the most popular ones. I don't have the Sanyos right now within reach, but those are also just fine. So there you go. It's a quick look at the SXB. I've got to do a couple of little fine adjustments to the driver. Couple of things about it. It is pot adjustable. It will have 2 ranges. It is continuous ground. It's boost only. Has very high switch. Well over 10 amps is all I'm gonna say. And it's over 15 amps. So you shouldn't have a problem basically running this driver at any current that we'll need for 445 nanometer for quite some time. I don't know what the price is going to be yet on this driver, but it's going to be within reason, like any of my other prices are. But yeah, let me upload this. When I get my 20 amp power supply in, I'll do a more proper video on this. But more real world test is when you do it with actual cells. And on top of that, these cells were old used cells, and it's performing just how the driver should be performing. But I'm glad I switched over to the larger package like I said I was, and it definitely has made a difference. So I'll see you guys later. Thanks.